Solution to EMC problems, surge protection components and filters, module 5.6. So, here we will describe gas discharge tubes, varistors, diodes and filters. Some very basic information will be covered. For more details, you can refer to other literature. So, devices can be protected against surge currents either by blocking or limiting the surge currents by a large series impedance. Or by diverting the surge currents by a small shunt impedance, or one can use a combination of both methods. So, while discussing the high frequency behavior of components, we have seen already some components suitable for blocking or diverting. Say for example, if you have capacitors, we have seen that capacitors can have very low impedance at high frequency. So, what is the characteristic of a surge? A surge will have a characteristic in which the rise time of the wave is very high. So, you have large frequency content in it. So, this large frequency content will be diverted through the capacitance, and if you connect a inductor in series, it will block, it will produce a high impedance for this highly varying transient. So, inductor can be a blocking device and capacitor can be a shunt device. Of course, in filters you are using a combination of both, but in addition to that there are some other devices also. So, they are metal oxide varistors. It is a special type of material with special nonlinear characteristics. Inductors and capacitors are linear, are having linear characteristic. They are frequency dependent, their impedance, but they are not dependent upon the magnitude of the current or voltage for their operation. So, they are linear devices, where metal oxide varistors and spark gaps are non-linear devices, because their characteristics are affected by the amplitude of the surge. So, metal oxide varistors, we will describe what it is, but some of the basic characteristics of those devices are listed out here. So, they are often called a clamping device, because it clamps. So, if you have a surge like this, let us say a clamping device will clamp the voltage to a certain level and will not allow to increase above that value. Now, spark gap or gas discharge tube is more like a crowbar device. It is like putting a crowbar across two wires and kind of short circuiting it. So, it means that when this is operating, then suddenly the impulse comes to 0 level or to very low value. Then after that is only this you will be coming. So, here it will be this, that is the residual value. So, in operation they are very different. Then this has got very fast response, metal oxide varistors, less than 0.5 nanosecond or so it can respond, and large energy absorption capacity is there, safely conduct large currents, few kiloampere for several microseconds. It is not very expensive, but due to the way it is constructed, it has got large parasitic capacitance. Often it is in the form of some sort of a disk. So, this large area, surface area, and 2 electrodes over here. So, this will introduce large parasitic capacitance, so 1 to 10 nanofarads, whereas spark gaps can conduct even larger currents, several kiloampere, but it will have low voltage in the arc mode. So, this is the arc mode, and here the voltage is very low. So, it means that even after the disappearance of the surge, the current will be shunted out, and that put a severe strain on other equipments. Sustained short circuit, that is follow current, and small parasitic capacitance. It is more like 2 metal electrodes in a tube. So, you have very less surface area and you have very small parasitic capacitance. However, for this to break down, you require large voltage to conduct, whereas metal oxide varistors can be designed even for very small voltages, and this is relatively slow to conduct. So, these are the differences between metal oxide varistors and gas discharge tubes. Then another device is basically a diode, avalanche diode or Zener diode. So, they also are clamping device like metal oxide varistors, but much less in power and voltage rating, and the parasitic capacitance is large like varistor. Silicon diode is another one, clamping device, again very low clamping voltage you can get. It is inexpensive and small parasitic capacitance. In addition, you have opto isolators for some signal transmissions and all, where opto isolators can be used, and isolation transformers are generally used in high voltage labs and other EMC measurements. So, these are series isolation devices. So, these are not really surge protectors, they are more isolation devices rather. Filters can be a combination of series or shunt devices, and you can even introduce nonlinear devices into a filter. Let us look at the VI characteristics of gas discharge tubes. So, the picture here shows that. So, this is the basic surge. Let us take a 1.2 microsecond rise time by 50 microsecond fall time curve. This is the voltage and this is the time. Now, as the voltage reaches certain level, suddenly the gas discharge tube will conduct, it goes down and reach the breakdown or arc sustaining value. So, this is the arc voltage, and at this point a current will be initiated, and that current rises up and it is shown over here. So, this current is quite large. Then for the gas discharge tube to turn off, either this current has to come below a certain threshold value for it to goes up. So, this is the volt current characteristic of a gas discharge tube, what is drawn here, and it is a representation of the same effect as per some other choice of axis, that is voltage and current. Spark over characteristic of gas jar tube. The time of operation for gas jar tube varies with the rate of rise of the transient. So, it is not constant time required for the operation. Similarly, the level at which the tube conducts is also different. That depends upon the rate of rise. So, gas jar tubes are often ceramic or metallic tubes in the presence of inert gas or some other gas like that. So, this is the response time in seconds. So, this is 10 seconds and this is 10 to the power of minus 8 seconds, and this is the rate of rise of the voltage, and spark over characteristics is like that. So, for near DC spark over, you need a long time for the gas jar to be subjected to this DC voltage. So, if it is a slowly rising waveform, you require less time, but it is at a higher voltage. Similarly, 100 volts per microsecond, only a fraction of a microsecond is required as response time, but the response happens at much higher voltage. Similarly, it goes. So, static spark over voltage is 230 volt and dynamic spark over voltage is greater than static spark over voltage. Dynamic spark over voltage increases with increasing rate of change of voltage, that is dV by dt. The response time decreases with increasing dV by dt. So, these are the inferences you can get from this picture. VI curve of a metal oxide varistor. So, this is non-linear. So, this is the operating region and some leakage current region, and this is symbol of the varistor. So, we can have a current versus voltage waveform for this also. So, in time domain you can represent it like this. Say for example, this is suppose your surge is going up like this, then varistor is operating, so it is clamping at this value, and this is the current through the varistor. So, you can take two operating points 1 and 2. So, I1 is k V1 to the power of alpha and I2 is k V2 to the power of alpha. Then alpha is log of I2 by I1 divided by log of V2 by V1. Metal oxide varistor can be modeled. So, suppose this is the ideal nonlinear part of the varistor due to the leads of the varistor. You have inductance and you have bulk capacitance also across the varistor, and that is this bulk capacitance, and bulk leakage resistance R leak. So, this is the clamping voltage. The actual voltage would have been like this. It would have been going like this and coming like that, or something like this. So, it is getting clamped and reduced. Now, the varistor model and high frequency model of a capacitor are quite similar, even though there are some differences. So, at high frequencies or with very fast rise times, varistors may behave like capacitors also because of that. Because this nonlinear element requires very large voltage to be impressed across it. But during high frequencies, lot of voltage drop can happen in the inductor itself. So, we will show one example of that. Now, here cascade protection. Often you will use several stages for protection, so that at each stage you are reducing the transient from the previous stage. For example, if this is your input transient, you have a spark gap, then after the stage 1, the current is the voltage transient is of this form, the clamping by spark gap. Then you have a MOV, so that is clamping the voltage. Then after that you have a diode clamping the voltage. So, you get very low values over here. So, in between you have inductors for coordinating the surge protectors. So, you require this because when a surge is coming, you want first this to operate, your spark gap to operate, so that maximum energy is bypassed. If it failed to operate and the surge is coming directly onto this diode, already equipment damage can happen. So, that is the reason why, to make sure that this is operating first, you have this inductors. Now, filters. As said before, often inductors and capacitance can be combined in series and parallel to form low pass filters, that is attenuating high frequency signals. So, filters can be used to attenuate any leftover low level but very fast noise from the last stages of protection. So, passive filters are frequency selective devices. So, you can just remove higher frequencies from the remaining current after the surge arresters and clean up the signal in the output. So, an RC network is shown here as a filter and a LC network is shown here as a filter. One drawback of filters is that it can introduce insertion loss even during the normal operation. For example, if this is the magnitude of the load voltage without filter and VLW is the load voltage with filter inserted, then the insertion loss is defined as 20 log VLWO by VLW, that is given by this, and with the filter with an impedance of ZF, the voltage across load with filter is given by this. ZF is the series impedance of the filter. Another example of a filter is a power supply. This gives protection against both common mode and differential mode electromagnetic noise. So, one example is shown here. So, L line, neutral and ground. So, you have a choke over here. Let us say this is the protector port, you have capacitors across all the lines. Now, CD1 and CD2, and this is CD2. And CC1 and CC2, CC1 and CC2. So, these divert common mode, CD1 and CD2 divert DM mode currents, that is differential mode, whereas the other one CC1 divert common mode currents. And usually CC1 equal to CC2 and is kept very low, about 2 nanofarad, to limit the leakage current to below 1 milliampere for safety reasons. And typical values of CD1 and CD2 are in the range of 0.1 to 0.5 microfarad. So, this is only one example. You can find several such examples in literature or at filter manufacturer's website. So, it will be interesting to look at them and see their designs. Now, previously I mentioned here that at high frequencies or with very fast transient rise time, varistors may behave like capacitors. So, that example is shown here. This is MOV subjected to fast transient experiments, sub nanosecond rise time, and this is one experimental data, and this is something simulated capacitor with same characteristic as experiment. The nonlinear zinc oxide element of the varistor is not subjected to high enough voltage to turn on due to the large voltage drop across the parasitic inductance. So, what it shows is that when varistor is connected and if you have very long leads and if it is subjected to extremely high extremely fast rise time voltages, then the drop across this inductor. So, this may be like a inductor. So, the inductive drop under extremely fast rise times will drop the voltage in such a way that this varistor will not be clamped. So, you do not get the benefit of the varistor if you have very long leads. So, that effect is shown over here. So, this is the non-ideal model and this is the ideal model and this is the injected current. So, that is why you have often have surface mounted varistors to eliminate this type of a problem. So, that the full voltage is coming across the varistor elements and the full non-linear characteristic of the varistor is playing into picture. Otherwise, varistor may just act like a high frequency capacitor and nothing more than that. So, that ends this part of the chapter.